Hi everyone, this is the sixth worksheet. So here we have the first question. We will decide if the given relations are linear, homogeneous or not. And then we will decide the degree if it is. So here we have a recall there. If we have a linear homogeneous relation, recurrence relation of degree k, then it should look like this, okay? So here we have C1, C2, they are real numbers, they are constant, okay? We have these A sub n minus 1 till A sub n minus k, okay? So this is the relation, which is linear. By linear, we mean we don't have something like A sub n minus 1 squared, okay? We don't have something like that. All these values are of degree or with power 1, okay? And by homogeneous, we mean we don't have something with n or 2 to the n, okay? We don't have something like that, okay? So here we have a sub n, okay? It's given by this. It is actually linear and homogeneous, right? It is given exactly as in this equality. So it is linear and homogeneous. What's the degree of this relation? It is 3. Okay, degree of this relation is 3 because here we have n minus k. Okay, the least in this. Okay, this is the least index, so we have 3 here. So the degree is 3. What about this? Here we have n, right? This is not constant. Okay, this depends on n, so this is not a linear homogeneous relation. And what about this? It is exactly what do we want? So here we have 4 as degree. What about this? Here we have some constant and no change here, right? No value with change. So we have, as we don't have any variable here and some constant only, this is not homogeneous. That's why it's not a linear homogeneous recurrence relation. What about this? We have here squared. That's why, again, it's not. And what about this? This is exactly a linear homogeneous relation, and the degree is 2. And this, as we have here n, it is not a linear homogeneous relation, okay? So we have only F with degree 2, C with degree 4, and A with degree 3, okay? So here we have second question. We will solve the relations, okay, together with the initial conditions given. So here we have a recall again. If we have this equality, we can write, instead of A sub n, we can write R to the n, right? We write it and we have this value. Then we divide it by R to the n minus k and get this equality, which is called the characteristic equation. So we have here r to the k minus c1 r to the k minus 1 which is equal to 0. Okay, this it's also called root characteristic equation. Okay, so the solution for this equality, for this relation, can be found by using this characteristic equation. Okay, we will first find this equation and find the roots of this equation, then we will write the general solution. Okay, so from this 2 star and star, we get that A sub n or R to the n is a solution of star of this, if and only if R is a solution of this. Okay, that's why we first find the roots for the characteristic equation. So here what do we have? We are given this A sub n which is equal to a sub n minus 1, where n is greater than or equal to 1, and a0 is 2. What do? We first find the characteristic equations, which is r squared minus, r squared equals to r, okay? So we solve this equality. We have r squared minus r equals to 0. We write it in the parentheses of r, and we get r1 equals to 0 or r2 equals to 1. Okay, we just denote it by r sub 1 and r sub 2. It means we have two roots for this equality. Okay, one of them is 0 and the other one is 1. Okay, so here for that one, for the general solution, what do? They are different roots, so we write it like this. Okay, here alpha 1 and alpha 2 are some constants. So for r1 we have 0, then we ignore it. Okay, we have multiplication, so we get 0 there. And for r2 we have 1, so we get alpha 2. Okay, so a sub n is equal to alpha 2. Okay, it means it is a constant sequence. Okay, you can see it like that. So a sub 0 is equal to 2. It's given here. So it means when we plug n equals to 2, n equals to 0, we get 2. So alpha 2 is equal to 2. Hence, we obtain a sub n is equal to 2. Okay. So here we have another recurrence relation. So n is greater than or equal to 2, and the initial conditions are given here. A0 is equal to 6 and A1 equals to 8. So we first find the characteristic equation, which is this. Okay, and so it can be written as in this form. So r equals to 2. Okay, so you see r equals to 2 of multiplicity 2, so we need to write it as in this form. Okay, for the first one we have alpha 1 2 to the n plus alpha 2 n times 2 to the n. If it was of multiplicity 3, for example, we would write plus alpha 3 n squared 2 to the n. Okay, it goes like this. So when n equals to 0, we have this. Okay, we just put n equals to 0 and get this value. So alpha 1 is 6, and we put n equals to 1 and get this equality. Okay, it's given here 8. So we have this. We just write for alpha 1 6 and obtain that alpha 2 equals to minus 2. Okay. Here we have the general solution. Instead of alpha 1 and alpha 2, we write their values and get this. So what about this? We're given this relation now. Okay, the characteristic equation is this, r squared equals to 1 over 4. And the roots are plus minus 1 over 2. We write again, as usual, okay, in this form. We just want to find alpha 1 and alpha 2 using these conditions. So we plug n equals to 0 and get this, and we plug n equals to 1 and get this. Okay, you can multiply the second equation and get alpha 1 minus alpha 2 equals to 0. Okay, when you add these ones, you get 2 alpha 1 equals to 1. So you get alpha 1 equals to 1 over 2. And again, you plug alpha 1 here and get the value of alpha 2. Then, as we know them, we can write here in this equation. So we get this, okay? Now we want to find the solution for this relation with these conditions, okay? Again, we write the characteristic equation, which is this. So if you have some polynomial of this third degree, you just first find a root. Okay, you just try 0, 1, minus 1, 2, minus 2. Okay, you just try a few one. Okay, so when you find one of them, for example, here we found minus 1 satisfies this equation, so minus 1 is some root. Okay, is a root of this function, this polynomial. So we have, this is one of the factors of this polynomial, r minus minus 1, which gives r plus 1. Okay, so you divide this polynomial by this r plus 1 and get this factor, the second factor of the polynomial. So here we have r plus 1 times r squared minus r minus 6 equals to 0. So we just need to find the roots of the second function, which can be written in this form. So r1 equals to 3 and r2 equals to minus 2. So here we have this general solution. So the first root was minus 1. So here we have minus 1 to the n. And the second and the third roots are 3 and minus 2. So each of them of multiplicity 1. So we have this. Now we just use these conditions. Okay, when n equals to 0, we plug n equals to 0 there and get this. Then 1, then for 2, we write them. And we solve these three equations. We add the first one and the second one. Okay, we find this, and second one and third one, we get this. So if we add them, we solve this system, we get these values. Okay, for when we find these ones, we plug them into 1 in the first equation and get alpha 1. Okay, so minus 1 to the n, the alpha 1 equals to 8, so we write 8 there. Okay, we find the values of these constants, so we write them. Okay, this is the general solution. Okay, for this one, we will write the general form. Okay, we don't have any initial value. Okay, so first we write the characteristic equation, which is this. Okay, if you multiply this, so if you divide this by r to the n minus 4, you'll get r to the 4, okay, you'll get this. You apply the first recall, okay, to find the characteristic equations. So you have r squared minus 4 to the r squared minus 4 squared equals to 0. So here we have r minus 2 squared times r plus 2 squared. Okay, you can write this one in r squared, r minus 2 times r plus 2. So you have this. Okay, here we have 2 of multiplicity 2 and minus 2 of multiplicity 2. So for the first one, for 2, we write as in this form. Alpha 1 times 2 to the n plus alpha 2 n times 2 to the n, because the multiplicity is 2, so we write n. Okay, for the second one, we do the same thing for minus 2. Okay, as we don't have any initial conditions, we just leave it like this, because we cannot find alpha 1, alpha 2, alpha 3, alpha 4. We cannot find these coefficients as we don't have any condition. Okay, so this is the general solution. Okay, for this one, here we see the roots of the characteristic equation. So we see minus 1 is written 3 times. So this is one of the roots and has multiplicity 3. And 2, for 2, this is one of the roots again, and multiplicity 2. We write the rest similarly. So the general solution should be like this. Alpha 1 minus 1 to the n plus alpha 2 n times alpha minus 1 to the n. And again, we multiply it by n because the multiplicity is 3, right? That's why we write it 3 times. Each time we multiply n, okay, by n. So for 2, we write 2 times, and for the second one, we multiply n. And for 5, again, we write it 2 times, and the second one, we multiply it by n. And the last one is unique. It's of multiplicity 1, so we have this. What about this? This is the last question, I guess. So first, we determine values of the constants a and b, such that an equals to an plus 1. There's a typo in the worksheet, so it should be a times n plus b, okay? So for this relation, what do we do? Here we have the solution. Sorry, I forgot to solve this part first, okay? Sorry. So here we have an plus b, and we have this relation. We just plug an plus b for a sub n, okay? Then for a sub n minus 1, we have a times n minus 1 plus b, okay, for a n minus 1. And here we have n plus 5, okay. So we solve this equality, okay. We just, on the left, we have a n plus b. On the right, we write each term with n in the parentheses here, and the rest as coefficient here as constant. Or so here the multiple of n should be equal to a here. So 2a plus 1 equals to 1, equals to a. And for this one, it's equal to 3, okay? We just solve these ones and we find a equals to -1 and b equals to -2. So this was the easiest part. So what's the solutions of this recurrence relation? So here we have, you see, n plus 5, it's not homogeneous. So what do? We first separate the general solution into two parts. One of them is homogeneous part and the second one is particular part. So for the homogeneous part, we do the things that we did before, okay? So we find characteristic equation, we find the roots, and we write it by this. So this is the homogeneous part. This is what we did before. So for the particular part, we write b sub n equals to cn plus d. Why do we do that? Because here we see the particular part is n plus 5. So this particular part of the general solution should be look like this, okay? So that's why we write cn plus d, okay? So we need to find this c and d. How do we find it? We have this bn equals to 2bn minus 1 plus n plus 5. How do we do that? Because we write, instead of an, we write bn, okay? This should be satisfying the star, okay? So we write, instead of an, we write bn. So what do we do? Now, instead of bn, here we have this equality. That's why we write cn plus d. And for that part, instead of n, we need to write n minus 1. So we get this, okay? So on the left, we have cn plus d, which is bn. And on the right, we have 2c plus 1 times n, okay, plus the constant part, okay? So this parenthesis should be equal to c. That's why we write it here. And the constant part should be equal to d. Now what do? We just solve these two equations and get these values. So the particular part then is equal to this, -n minus 3, okay? So this is the particular part of the solution, and we did before for the homogeneous part. So Hn, the general solution, is equal to this, okay? The sum of these parts. So we now find the solution for A0 equals to 4, okay? Now, what do? We know already the general solution, so we just plug n equals to 0 and obtain this. When we write n equals to 0, what do we have? A0 equals to, we know it's equal to 4, so 4 equals to, here we have alpha 1 minus 0 minus 3, here we have alpha 1 minus 3, so alpha 1 equals to 7. Then a sub n equals to, we had only one coefficient that we don't know, so we already found it. So a sub n equals to 7 2 to the n minus 3, okay, when a0 equals to 4. So we did before the first part, but that's all. So good luck for the exam. See you.